This tutorial presents the possibility to introduce nonlinear relation between force and strain in membranes in AquaSim. Linear elastic materials are the basis for AquaSim. However, nonlinear relations between force and strain can be introduced to component types such as membranes. Having completed this tutorial, you will be able to know the basics of nonlinear data tables in AquaSim, which is often abbreviated N.L.D. Establish a simple model with a nonlinear membrane, and evaluate and self-validate results in AquaView. To introduce nonlinear membranes in AquaSim, one establishes tables with a relation between axial force and strain. Such tables are possible to implement for membrane components, type normal. Generally, linear material behavior looks like this, where you have a linear relation between axial force and strain. When the material behavior becomes nonlinear, the relation may look like this, where the relation no longer is a straight line. Let us exemplify a nonlinear relation with this table. For the individual rows in the table, you will have the following relation between strain and elongation. L0 is the initial undeformed length of the membrane, and epsilon is the strain. If we consider the first row in the table, then an axial force of 100 Newton will elongate the membrane 0.1 meters per meter. Assuming the membrane panel to be 10 meters, the elongation of the membrane become 1 meter. Let us consider a case study in AquaSim. Technical data for a simple membrane model is given in this table. When applying nonlinear relation between force and strain, it is recommended to validate the input data on a simple model, like the one presented here. The membrane has a height of 10 meters, a width of 10 meters. The thread diameter is 2 millimeters. Having a mask width of 1 meter and total length of threads in vertical direction 100 meters, the number of vertical threads will correspond to 10. In each corner of the panel, point loads are added, each of minus 12,500 Newton. In this AquaEdit model, the same membrane panel is shown. The two top nodes are restrained from moving. This is seen by the blue nodes in the top here. At the lower end nodes, two conservative point loads have been added. Double-click on the component to view the material properties. Here you may recognize the input from the table. The table for nonlinear data is found at the bottom, in the Advanced section. To create a new table, you can select the drop-down menu and select New. In this case we prepared a table called NLD0. To open this, select the three dots to the right of the drop-down menu. Name gives you the option to type a name free of choice. Default is that the first table in your model is called this. The strain thread Z is where you input the strain. This is a unitless quantity and defines the elongation per thread length. 1 means the threads will stretch 1 meter per meter. Axial force is the force at the given strain. This is the axial force in the threads. As default, AquaSim assume that the input for strain Z and axial force is equal in both local directions of the membrane panel. But the user can choose to have different relations in Z and Y direction. This can be done by selecting the checkbox for anisotropic. 4 rows, with 4 relations have been established. In the lower section of this table, you may add or remove rows. Applying nonlinear tables in AquaSim, the user should be aware of some things. The strain-axial force relation should be increasing for increasing axial force. Depending on the loading situation, it could be wise to define relations for strain and force below zero as well. Combinations of positive strain and negative axial force is not recommended. The table should be within the range of expected forces. And at least 2 rows are required to establish a nonlinear relation. Note that in our table, it is said that for a force of 2,500 Newton, a strain of 0.1 should be applied. This will result in an elongation of 1 meter for each vertical thread. We should run an analysis and check the results and compare with the table input. Let us exit the table and go to the Export menu. As the loading situation is considered static, it is only necessary to include the initial steps of the analysis. Hence, we may set num total steps for waves to 0. This will omit the dynamic part of the analysis. OK. So let us export the model and run the analysis. Load the AVZ file in AquaView. Let us first examine the axial force in each vertical thread. This result option is found under Net and Axial Force in Vertical Twines. In the AquaSim literature, the membrane threads may also be referred to as twines. Right-click on your panel to view the forces. As we can see, the force in vertical threads is 2,500. Remember that from the nonlinear table, we said that for 2,500 Newton, this should give a strain of 0.1 meter per meter. So, we plot the elongation of the vertical threads. This is also found from under the Net menu. This option presents the elongation of each thread in percent. The membrane has an original height of 10 meters. 10% of 10 meters is 1 meter, so the elongation should correspond to this. To view the elongation, we can plot the displacement of the membrane in z direction. Now that we see there is a logic connection between the input and results, we are ready to apply the nonlinear data table to a physical model. It should be noted that introducing nonlinear material properties will influence convergence of the analysis. Usually, it is more challenging to achieve convergence the more nonlinear the material behavior is. All files presented here, and more, is available online at our website. Visit us at aquasim.no for more videos.